Stress control for cable termination. We have a middle voltage single core cable here. To access the conductor, you need to remove several layers: the jacket, the screen, the insulation, and the place where the screen is removed concentrates the electric field stress. To reduce the stress value, the yellow stress relief mastic is applied. And in this example, I'm going to simulate two cases, with mastic and without mastic, and compare the results. Cable operates at AC voltage, but I'm interested only in the peak value of electric field stress, so I'm going to apply DC voltage. Okay, let's start QuickField now. In QuickField, I create new problem. Cable. Next. Problem type is transient electric. Cable features rotational symmetry, so the model class is axisymmetric. Length units are millimeters. Next. As I'm going to simulate the cable at the DC voltage, I can specify any values of the time steps here. Let's simulate the period of 1 second with the time step of 0.2 seconds to let the electric field to propagate and stabilize. Finish. On the left is the problem pane, and on the right is the geometry model editor window. In axisymmetric problems, the axis of rotation is a horizontal one, and I should draw only the upper half of the cross section. Cable conductor diameter is 20.4 millimeters, so I'm going to insert a rectangle. I will simulate the short piece of the cable, just 100 millimeters in length, with a diameter of 20.4. Insert. Close. Zoom to fit. This is the cross section of the cable. The insulation thickness is 8 millimeters, so I will insert another rectangle with the width of 100 millimeters and the height of 36.4 millimeters. Okay, this is conductor, this is insulation. Next, we have the screen, and the screen thickness is 0.5 millimeters, so I insert another rectangle. This would be the screen, and the cable outer diameter is 52 millimeters. Insert. Okay, now switch to insert mode and cut the insulation and the screen. And I should draw the horizontal axis. Next, switch to select objects mode and remove all objects located below the axis of rotation. Zoom to fit, remove this edge, and remove this edge, and remove this edge. So when you terminate the cable, you cut off the jacket and you cut off the screen. When the cable will be connected, here you would use the insulation tape or insulation tube to make new insulation. So I'm going to draw here these lines, and this would be the new insulation. Okay, let's assign labels. For labels, you can explain the geometric object's meaning and provide the physical properties. Switch to select objects mode. Click here, this is conductor. This is insulation, XLPE. This is jacket. This is new insulation. And this is screen. And here we have the air. Let's zoom out, switch to insert mode, and draw the air block boundary. This is air. Okay, now let's provide physical properties for these labels. Double-click the label name in the tree. Electric permittivity of the air is 1. For the XLP, electric permittivity is 2.5, and electrical conductivity is 10 times to the power of minus 15 Siemens per meter. For the insulation, for the jacket, electric permittivity is 2.5, and electrical conductivity again 10 to the power of minus 15 Siemens per meter. And the same for the new insulation. For the conductor, there is no electric field inside the conductor, so I do not specify any properties here, just click OK. And you see the exclamation mark next to the label name. That means that the electric field will not be calculated in this block. Instead, I'm going to assign label to the conductor surface. And for this label, I will specify the electric potential. Now the cable operates at AC voltage of 33 kV, 33,000 volts. This is the root mean square value, and the peak value is times square root of 2. You can type in the sine function here as well. 360 degrees multiplied by the frequency multiplied by the time. But I'm interested only in the maximum value of the electric field stress, so there is no need to simulate entire process. I will simulate only the moment of time when the electric potential is maximum. Okay. For the screen, again, I do not specify any value. Instead, I will assign a label to the screen surface for the edge, label 0. And for this label, I specify 0 electric potential. Geometry model and the data are ready. Before I start the analysis, I should build the finite mesh. Just press this button and the mesh will be generated. Now save all problem files and solve the problem. Here you can see the results. This is the electric potential distribution. And I'm interested in the electric field stress. Let's zoom in. The peak value of the electric field strength is 14.7 kilovolts per millimeter. And the location is here where the screen is cut off. You can use the local values tool. Click any point and get the exact field parameters, or you can use here below the status bar and see the electric field stress in any point. You can also use the contour tool. Click here and here to select the insulation surface. And then for this contour, you can see the contour line here. I can get the field distribution on the XY plot. This is the place where the screen is terminated. And the exact values I can get in the table. Coordinates, electric field strength. Okay, let's copy this picture and paste it here in the Word document, just to remember. Now, there is a way to reduce this electric stress. If you search for the cable termination instructions, you will learn that the yellow stress relief tape is applied. Let's add the yellow tape to the model. Let's zoom in and switch to insert mode. Tape covers the area 10 millimeters to the right and 10 millimeters to the left. So I'm going to follow these instructions. You can see the current coordinates here at the status bar. 10 millimeters to the right. And then 10 millimeters to the left. Okay, switch to select mode, select and remove unnecessary parts. Remove this line, click here. This would be the yellow tape. And this tape features electric permittivity of 15 and nonlinear electrical conductivity. Electrical conductivity is a function of the electric field stress. Here I have the dependency in the text file. I just copy it and paste it here. And to improve the problem convergence, you see the conductivity rise is too steep. I will artificially limit the rise speed and add 2 points here. The electric field strength that we currently have is 1.5. It's somewhere here. So these 2 points doesn't affect the solution, but they help the problem to converge faster. Okay. Again, build the finite element mesh and solve the problem. Switch to the electric field strength. Now, the peak value of the electric field strength is 9 kilovolts per millimeter. It was 14 before. Again, let's build the contour here. Click to select the edge, click to select the edge, and click to select this edge. XY plot. Now, thanks to the stress relief tape, we have reduced the electric field stress from 15 to 9. 60% of the original stress value. If you search for the stress control for the cable termination on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the result pictures, and download the simulation files. Simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition, that you can download from our website for free.